All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is Advanced Gas Laws. We are going to need a calculator and a periodic table for this one, so if you don't have those handy, go ahead and pause the video and we will begin. So here we go. What do we mean by Graham's law of effusion and diffusion? So let's start with the concept of diffusion. What do we mean by diffusion? Well, diffusion really means the movement of a gas through an open medium, an open space. Let's take, for example, a situation in which we have maybe a container of perfume. So that'll be my container of perfume. And of course, in the bottom of the container is liquid perfume. But I open the lid, and by the way, this is a person's nose. That's their nostril there. And I open the perfume, and what's going to happen is that the particles are going to begin to diffuse. Now, they're going to diffuse in all directions, obviously, right? But eventually, what's going to happen is that those particles are going to reach the nose, the olfactory nerves of that individual. And they're going to be able to smell that perfume. And we call that phenomenon, we call that diffusion, all right? And Graham has a law for diffusion, and we're going to talk about that law in just a moment. But we want to also discuss, before we go on, the concept of effusion. I'll draw a line just like that to differentiate diffusion from effusion. What effusion is a special situation in which we have a container. And the container, this is just a box that looks kind of like that. And the container is separated by some type of a barrier, right? So I'll just draw a barrier just like that. But just right in the middle of the barrier is an opening. So I'm just going to, with a little blue mark, open up a little hole. That's a pinhole. And on either side, or actually on one side of this little contraption, we're going to put gas molecules. So it doesn't matter what type of gas this is. We simply have gas particles on one side, but not the other. In fact, the right-hand side of this is a vacuum, all right? It has nothing in it. So what we're going to do is we're going to measure the rate at which these particles, which are going to be bumping into each other and bumping into the container, that's the nature of gases. Eventually, one of them is going to make its way through the little hole, and it's going to end up on the other side. And we want to know how long that takes to happen. We call this phenomenon on the right-hand side, this phenomenon is called effusion. Not diffusion, but effusion. All right. So Graham had something to say about the relationship between the velocity of different particles, different types of particles or sizes of particles. And here's what he said. He said that if you have two different gases, we'll call them gas 1 and gas 2 for lack of a better term for right now. We'll just say 1 and 2. If we have two gases, V1 and V2, or I should say gas 1 and gas 2, that have two different velocities, V1 and V2, we can compare those two velocities. One is moving faster, presumably, than the other, and we can make that comparison. And we can compare them through their molecular weights. And so what Graham said was that the velocity of one gas was related to the velocity of a second gas by the square root of the inverse of their molecular weights. That's critical. The inverse of their molecular weights. In other words, the heavier the particles, the slower they move. The heavier the particles, the slower they move, and vice versa. The smaller the particles, the faster they're going to move, right? So let's put this Graham's law of diffusion to the test. Let's look at number 1. Number 1 says, what is the ratio of the average velocity of neon atoms to krypton atoms at the same temperature and pressure? So we're looking at two different types of atoms here, neon, krypton. All right, those are the two gases. Now, neon and krypton are both unimolecular. In other words, those gases are not diatomic, like, for example, nitrogen gas or oxygen gas. They're unimolecular. So we want to compare neon to krypton, their velocities, relative velocities. So here's what we're going to do. Graham's law says V sub Ne over V sub Kr is equal to the square root of the inverse, don't forget that, the inverse of their molecular weights. So the molecular weight of krypton over the molecular weight of neon, then take the square root of that. We're going to just look on the periodic table for their molecular weights, and we get for krypton 83.80, for neon 20.18. right? And when we do that, we get this number. We get 2.038. What that means is that neon is moving a little more than twice as fast as krypton. On average, a little bit more than twice as fast. And that makes sense. It's a smaller molecule. It's a smaller, or I should say a smaller particle. It's not a molecule. It's an atom. But it's a smaller atom, right? It's a smaller particle. So 2.038 is the ratio of those two particles, of the velocities of those two particles, and that'll give us number 1. Let's look at number 2. Number 2 tells us that CO2 molecules have an average speed of 25 meters per second at a given temperature and pressure. Now, that's not to say every single one is moving at 25 meters per second. Some are moving a little faster, some a little slower, but on average, 25 meters per second. What is the average speed of carbon monoxide molecules? So this time we're looking at CO of carbon monoxide molecules at the same conditions. So let's see what we know. VCO2, we've been told, is 25 meters per second. We're looking for the velocity of carbon monoxide, so we'll put a question mark right there. Let's set it up. Velocity of carbon dioxide divided by velocity of carbon monoxide is equal to the square root of the inverse of their molecular weights. So it's the molecular weight of carbon monoxide divided by the molecular weight of carbon dioxide. Notice they're inverses, right? So now let's plug things in. We've got 25 divided by the velocity of carbon monoxide is equal to, let's look up those molecular weights. For carbon monoxide, it's 28.01. But for carbon dioxide, it's 44.08. We'll take the square root of that quotient, and we get this, 0.7978. Now, we want to know the velocity of CO. So we'll just do a little algebra. We'll pull the velocity of CO up, 0.7978 down, and here's what we get. 25.0 divided by 0.7978, and this is the value, 31.3 meters per second. Notice that it is a bit faster than is the carbon dioxide. That makes sense. It's smaller. Smaller particles move faster. That's Graham's law. That'll do it for number 2. Let's move on. Number 3 deals with density and molar mass. These are very important problems right here, numbers 3 and 4. So let's take a look. It says, what is the molar mass of a gas if its density is 3.2 grams per liter at 15 degrees Celsius and 2.17 atmospheres? So we're going to use what we know to determine the molar mass. But let's just review what molar mass means. It means the mass of something divided by the number of moles, right? It's grams per mole. So if we can get to grams and we get to moles, then we can divide those two and it'll give us the molar mass. So here we go. PV equal nRT is the ideal gas law. We want to solve for the N. So N is equal to PV divided by RT. Let's plug in. The pressure we're told is 2.17 atmospheres. Now watch this little trick. I'm going to assume a volume of 1 liter because later on I am told that the density is 3.20 grams per liter. So later on I'm going to use the 3.20 grams so I can use the 1 liter on the bottom. So that's the volume. I'm saying if we were at 1 liter, this is the number of moles that you would have. So 0.0821 liter atmospheres per mole per degree Kelvin is the R value, and we've got 288 degrees Kelvin. Don't forget to add 273 to 15 to get this number. And here's what we get, 0.092 moles. So we have half of this problem done now. That's the number of moles of gas we have. Now we just have to know what the number of grams is. Well, they're telling us that if you have that volume of 1 liter, and we've set it up to do that, 3.20 grams is the mass. So the molecular weight, or the molar mass, then is 3.20 grams divided by, is calculated 0.092 moles. When we do that, we get 34.8 grams per mole. That is the molar mass of this unknown gas. So we've determined it using the density of in grams per liter, 34.8 grams per mole. Let's look at number 4. What is the density of CO gas if 26.32 grams is at 302 Kelvin and 98.9 kilopascals? All right, so let's take a look at this. First, we have 26.32. Sorry for that, I neglected the 2. I had to put it up here. So it's 26.32 grams over 1 times 1 mole Just look it up on the periodic table. Just add up carbon and oxygen, 28.01 grams. So these two are going to cancel away, and I'm going to be left with 0.939 moles. Now let's use PV equal nRT because I know the number of moles now. I'm going to solve for volume. Volume then is equal to nRT divided by P. The N we've just determined is 0.939 moles. The R we're going to use is 8.314 cubic decimeter kilopascals per mole per degree Kelvin times the temperature. The temperature is 302 Kelvin. Remember, it has to be in Kelvin degrees, and it is, so that's good. Divided by the pressure, 98.9 kilopascals. It's in kilopascals, so that's why we use the 8.314. When we do that calculation, we get 23.8 cubic decimeters. So now let's finish the problem. Remember, density, we've always been taught, is mass per unit volume. We know the volume now to be 23.8 cubic decimeters. What is the mass? The mass is 26.32. 26.32 grams. Sorry that 2 is so small, but that's what it is. 26.32 grams per 238 cubic decimeters. Our density then is going to be 1.11 grams per cubic decimeter. That'll do it for this one. Let's go to the next one. All right, the next one is going to involve stoichiometry, gas stoichiometry. So here's what we've got. It says find the volume of, in cubic decimeters by the way, of H2 at 24 degrees Celsius and 99.8 kilopascals produced if 5.90 grams of zinc reacts with excess hydrochloric acid. So what we're going to do is start with what we know. We've got 5.90 grams of zinc over 1 times, we're going to convert that to moles of zinc. That's what I've done right there. And then we're going to do a mole-to-mole bridge to hydrogen gas. All right, so now I'm left with moles of hydrogen gas. Now what I'm going to do is this. I'm going to determine the volume at STP, at standard temperature and pressure. I know that any gas, including hydrogen, has this volume, 22.4 cubic decimeters at STP. So when I do that calculation, I get 2.02 cubic decimeters of H2 at STP, at standard conditions. 0 degrees Celsius, that's the temperature, 1 atmosphere of pressure. Now I've established one volume for a certain situation, so now I'm going to use the combined gas law. P1V1 over T1 is equal to P2V2 over T2, right? All right, so now what I'm going to do is I'm going to solve for V2. P1V1 T2 over T1 P2, right? So here we go. What I'm going to do is I'm going to consider the first situation to be standard conditions. So the T1, the V1, and the P1 to be standard conditions. So let's go. P1 is, I'm going to do this in kilopascals, so 101.325 kilopascals times V1, which is 2.02 cubic decimeters. I just calculated that right there, times T2, 297 degrees Kelvin. I'm looking for a different temperature. 24 plus 273, 297, divided by T1, which is 273. Remember, at standard conditions, it's 0 degrees Celsius, 273 Kelvin, is equal to 99.8 kilopascals. That gives me a total, or after I calculated 2.23 cubic decimeters. That will do it for number 5. Let's take a look at number 6. What volume of O2 at 17 degrees Celsius and 745 millimeters of mercury is needed to burn 68.7 grams of C3H8 to produce CO2 and H2O? This is a combustion reaction. So first we'll balance. It's a 1 to 5 to 3 to 4 mole to mole to mole to mole relationship. I'm going to start with what I know, 68.7 grams, 68.7 grams of C3H8. Then what I'm going to do is I'm going to convert that to moles. 44.11 is the total. It's a 5 to 1 mole to mole ratio, and I'm going to figure out what the volume is at STP. 22.4 liters of oxygen gas at STP. That gives me 174 liters of O2. P1V1 over T1, P2V2 over T2. I plug in, I get 189 liters of oxygen. That'll do it for this one. I'll see you in the next one. Thanks.